Hi, this is Dr. Pello with video 3 of how to take correlations and translate them into latent variables and latent variable models. So we've been working with an example where we are estimating a latent variable called authentic living based upon 3 items from a scale that measure authentic living. And we've been noting those as variables 1, 2, and 3. And we've already solved that in our previous videos and found that the factor loadings for a unweighted least squares regression, unweighted least squares estimation is 0.75, 0.83, and 0.85. This estimation strategy is not exactly the same as maximum likelihood estimation, but in this simple case, I believe that the estimates would be the same. We can check that out later. The more complex your model, the more the estimates are going to diverge some. But overall, this is going to tell you how things work. In order to solve this problem using Excel, you're going to need a tool to start off with. And so if you don't have that, once you go to in Excel to File, go to Options, go to Add-ins, go to Excel Add-ins, and make sure yours probably starts off without these clicked. Click the Analysis Tool Pack, the Analysis Tool Pack VPA, which we're not using right now, but those are really cool. Has ANOVAs, regressions, various types of analysis that you can do. We want the solver add-in, and then go ahead and hit OK. Once you do that, once you go over to Data, you should notice a Data Analysis tab and a solver function. This solver function basically does the same thing as calculus. It will minimize a function and it will maximize a function. And what we're going to do is we're going to show you how to minimize a function that is key to understanding how structural equation modeling operates. So, in order to do this, what I want to do is reprogram what I have here. So, we are going to start off, as we've talked about before, with known information, so actual correlations that we want to estimate. So the actual correlations I want are 0.624 is the correlation between variables 1 and 2. 0.639 is the correlation between 1 and 3. And 0.708 is the correlation between 2 and 3. So I've taken my correlations from a previous correlation matrix. This is my known information. That's what I'm starting with. Over here, I'm going to start off by just putting in as placeholders path coefficients or estimates of these 3 factor loadings of 0.5. So I'm calling this A, this B, this C, and note that over here, A, put my A over here, A, B, C, and we know from what we've already previously done in Amos and with the algebra that A, B, and C should be the loadings of 0.75, 0.83, and 0.85. But over here, I'm starting with saying, here's my loadings, here's my 3 loadings, A, B, and C, and I'm just going to call them 0.5, 0.5, and 0.5. We now use tracing rules to give us implied correlations. So I'm going to rewrite these. Go ahead and take these out. Okay, so The implied correlation between x1 and x2, I'll go ahead and write that here, 1 and 2, 1 and 3, 2 and 3. Okay, between 1 and 2, I would go through path A and multiply it times path B. So I'm going to say that is equal to this cell, path A, multiplied by this cell, path B. The A's and B's here are simply labels. These are the actual estimates, and these are the implied correlations based upon multiplying, in this case, 0.5 times 0.5 for my placeholders for A and B right now. For A and C, I'm going to go over here to A and multiply it times path C. And for my last one, B and C, I'm going to go over here to B and multiply it times C. So these are my implied correlations. These are my actual correlations, and my implied correlations are fairly decent ways off from the actual correlations. Now what I'm going to do is I'm going to specify how far they're off, and I'm going to specify that as a function of error squared, just like we did in regression. So differences squared. But instead of having data points away from a regression line or a response surface, I instead am going to think of error in terms of to what extent are my implied correlations that are driven by my model different than the actual correlations that I'm trying to reproduce. And so over here, I'm going to write equals the actual correlation between 1 and 2 minus the implied correlation between 1 and 2, and then I'm going to square that. No need for me to keep rewriting that. I'm just going to copy that function, paste it down. So this one's doing the same thing for taking the 0.639, comparing it to the 0.250, and squaring that, and then here the 0.708 and squaring that. Finally, here I'm going to sum the error squared. Okay? Now I have my model set up. As we saw before, least squares estimation seeks to minimize this our function. And our function is the sum of the differences between the implied correlations and the actual correlations squared. And so what I'm going to do to solve this is I'm going to go to Data, Solver. And you'll notice that it gives me languages here in the language of calculus, maximizing and minimizing. I want to minimize this cell right here, the sum of that error squared. I want it to be as small as possible. And I wanted to do that by changing these three path estimates represented here. I have 0.5s in here, but I want it to change it, hopefully, to 0.75, 0.83, and 0.85 as it seeks to minimize the error squared. Right? It's all set up, solve, and I did something wrong because I changed those up. There, I think that does it. Yes. There we go. And it reduced my error essentially down to 0. I think if you followed it far enough along, well, I have it rounded off, apparently. It's not perfectly 0, but it's 0 to enough digits and I get 0.75, 0.831, 0.851, the exact same estimates that I got from Amos when I did unweighted least squares. And you can go into SPSS and do a factor analysis of these data and specify unweighted least squares estimation, and you're going to get the same thing. So I've done no special weighting for each one of these differences. I've captured the differences between the actual correlation and the implied correlation. And in this particular model, there's actually a perfect solution. And so I am able to minimize it to where there's zero errors and get estimates that perfectly match what I got from the algebra. And there you see, that is how latent variable modeling works. One little added thing here, when you start getting into really fancy, complicated models, sometimes those models won't work. And people will say, you might need to alter the start values. What are start values? You don't see this as the programs get more sophisticated. You don't see this as often, but you can still run into problems occasionally. And my start values were 0.5s. Those were start values. Let me change these start values to kind of ridiculous numbers. Okay, here I have start values. Remember, these start values should represent, theoretically, the correlation between the latent variable and the measure. And these are not what we would consider reasonable correlations. Gives me a huge amount of error. Let's go ahead and see if the solver can solve this. So data, solver, it's still trying to minimize this function, solve, okay. Oh, it actually managed it. It's kind of hoping that it wouldn't. Let me try another one. 10 minus 5 minus 100. I did this successfully before. We'll see if I can do it again. Solve. Oh, look at there. This solution is not what we would expect. It's a really odd solution, right? You have a 10 instead of a correlation. And so this is a place where you could essentially get an estimate that's estimates that are really wrong and don't fit our theoretical expectations of correlations between latent variables and their measured variables. And when that happens, people will say, well, put in new start values. If you're a novice, it's just like, what do you mean? What are the values that I'm supposed to put in? Basically run some type of simpler analysis that uses an estimation strategy that is not as onerous, like principal components analysis is not as onerous as most factor analysis techniques, and plug those in. Or just take guesses as to the actual correlations of, 0.5s, 0.7s, and so forth. Data, solver, boom, and you're there. That is least squares estimation of a latent variable model. We'll see you for the next video. Bye.